Hi class, this is Mr. Morris. I'm making this video as kind of a backup for those of you who were not present on Friday. Also for those of you who were maybe a little bit confused as we went through it. This is a complicated process. So just making this optional video to walk back through the first problem, and then I'm going to try to walk through the second one as well. So if you will look at this, these notes, they're isotope abundance calculations. Yesterday what we did, on Thursday what we did is we looked for the atomic mass and we used the abundance to find it. Abundance is just another word for turning a percent into a decimal. So abundance is like the decimal version of a percent. So the way we find atomic mass is we multiply the abundance of your first isotope times the mass of that isotope plus the abundance of the second isotope times the mass of the second isotope plus, and you could do the same thing with third, fourth, however many isotopes you have. Well, it's not so bad when you know all of this information and you're only looking for one thing. It gets a little bit more challenging when you're looking for two things, which is the case when we're looking for isotope abundance. I'm looking for the abundance of the first isotope and the abundance of the second isotope. So in these problems, we're looking for two different things. So we need to use something called substitution, which is a tool you can use in algebra. So I've got like three different things that we're going to be doing with these problems. And the first one really is just getting organized with the data so that we would know how to use it. I've got the atomic mass, abundance, and mass. Abundance and mass. Those are the things we need to kind of get down. And we also want to know which substance we're dealing with. So what I want to do is make a table. Name, abundance, and mass. I'm just going to make a little table here for me to refer to as I go through the problem, make it a lot easier to follow what I'm doing. First thing I want to do is, what are the two isotopes we're dealing with? We're dealing with copper 63 and copper 65. So I'm just going to shorten that and say Cu63, Cu65. Those are the two names. I don't know what the abundances are, so I'm just going to come back to that in a minute. But I want to calculate the percent abundance, what I'm looking for, of copper 63 and copper 65. If the atomic mass is this, okay, well there's our atomic mass. Okay, that's not the mass of 63 or 65, it's the atomic mass. So let's just write it over to the side. Atomic mass equals 63.546 AMU. Okay, that's going to be important because it's part of our formula. Okay, we have the exact masses of these isotopes. Isotope 63, copper 63, has a mass of 62.93 AMU. So we're going to write that right here, 62.93. And then copper 65 has a mass of 64.93 AMU. All right. Well, that's great. I've got my atomic mass, got my mass numbers. The part I'm missing is abundance 1 and abundance 2. Those are the things I don't know. They're two different things. We don't know if they're the same or not. Probably not. So we're going to call them X, that's our first unknown, and the other one is Y. Now, any 2%, if there's only one isotope, and that's what it says right here, we're going to assume there's no other isotope. That means all of the copper in the world is one of these two isotopes. So if we're talking about percents here, we could say this percent plus this percent would add up to be 100%. Since we're talking about abundance, that's turning a percent into a decimal, 100 written as an abundance is actually not 100, it's 1. So if we were to write 100% as a decimal, you just write the number 1. This is useful because now I know X plus Y equals 1. I want to substitute something here in terms of X. And hopefully it'll make more sense as we go through this. And so we know, we just said that x plus y equals 1. Since x plus y equals 1, if I want to solve for y, I could do that. I could say y equals, if I want it by itself, I need to subtract x on both sides. So y equals 1 minus x. Okay, so now I can write y as 1 minus x. Now there is something I can actually solve. Now we're ready to set up our equation. The equation that we're trying to write down is based on what's up here. The atomic mass, which is 63.546, equals abundance 1 times mass 1. So abundance 1 in this case is x times mass 1, 62.93. So atomic mass is abundance 1 times mass 1 plus abundance 2 times mass 2. Abundance 2 is 1 minus x plus 1 minus x times 64.93. All right, now we need to do what they call in math. What we need to do is combine like terms. Not yet, I'm sorry. We need to distribute. So I'm going to leave this pretty much the same, but I need to distribute this out. So we're going to put 63.546 equals 62.93x plus, and then 1 minus x times this, well, I got to distribute. So 64.93 times 1 is 64.93 minus 64.93 times x is 64.93x. Now we would combine like terms, so that means all the x factors will be combined and the non-x factors will be combined. I'm going to start with the x factors. For this part, you may or may not want to use a calculator. That's up to you. But when you subtract these, 62.93x minus 64.93x, you're going to find that you get negative 2.00x. This is still 63.546. We haven't touched that number yet. And this is still 64.93. Now I want to combine like terms again. This time I'm doing 63.546 minus 64.93 so that the x factors are on the right side and these are on the left side. When you do that, 63.546 minus 64.93, you get negative 1.384. Equals negative 2.00x. Okay. Now I want to solve for x, so I need to divide by negative 2.00. So again, in the calculator, negative 1.384 over negative 2.00. We get 0.692. All right, but the problem actually asked me for the percent specifically, so I need to turn 0.692 into a percent by 100. Okay, so 0.692 gets multiplied by 100, so we end up with 69.2%. Okay. Now, I need to find what y is. See, this is my percentage of Cu63. If you look back at the table, copper 63 is X. So X equals 69.2%. Okay, now I need to know what Y is. Y equals 1 minus X, which is 1 minus 0.692. 1 minus 0.692, 0.308. And now we need to multiply that by 100. You end up with 30.8%. And that is copper 65. Okay, so recapping, first thing you need to do is figure out what it is you know in the problem and put it in a table. Write your names and the masses. Your abundances are going to be X and Y. Y is 1 minus X in this case. It's 1 minus whatever the other components are, whatever the other percentages are. Then you set it up in our equation. Atomic mass equals abundance 1 times mass 1 plus abundance 2 times mass 2, and so on. Then we just we distributed, then combined like terms. Then divided, solve for X, turn it into a percent, solve for Y, and turn that into a percent. Okay, so let's move down and look at the other one. This other problem is slightly different because we have 3 pieces of information that we need to deal with. So name, abundance, mass, just like before. This time we actually have 3 isotopes. We have magnesium 24, magnesium 25, and magnesium 26. Okay. We know the masses of all 3, so let's get those down. The magnesium 24 is the most abundant isotope. It has an exact mass of 23.985. If the atomic mass of magnesium is, okay, so there's atomic mass, let's write that down. (24.305). And this is what it asks for. What are the percent abundances of magnesium 25 and magnesium 26? And then it gives us masses. The mass of magnesium 25 is 24.986. And magnesium 26 is 25.983. Now, we have 3 abundances. One of them is given in the problem, this one right here. Of course, you need to turn that percent into a decimal. So move the decimal to the left 2 spaces or divide by 100, however you like to think about that. That's magnesium 24, that is 0.7870. That's our abundance. Then we have X and Y. All right, judging by what we just did above, we know that if we add all those together, it should equal 1. So this plus this plus this should equal 1. So 0.7870 plus X plus Y equals 1. So now if I want to solve for Y, say Y equals 1 minus 0.7870 minus X. So really what we need to find out is what is 1 minus 0.7870. You get 0.213. So 0.213 minus x. Y equals 0.213 minus x. Okay, so same concept as what we did up here, but instead of being 1 minus x, since I have another abundance given, it's 0.213 minus x. But we're going to set it up the same exact way we set up the other problem. We are going to write down our atomic mass, and I'm going to write down here because it takes kind of a lot of room. So we're going to write 24.305 equals this times that times 23.985 plus x. Sorry, there was a little glitch on the computer there. So again, we do the atomic mass 24.305 equals abundance 1 times the mass 0.7870 times this plus x times 24.986 plus 0.213 minus x, and then we multiply that by 25.983. Okay, now we got some more numbers to deal with, but we're still going to solve this the same way we did above. We start by distributing. So let's just kind of clean this up on this side. 0.7870 times 23.985, you get 18.88. That's what we get when we multiply those. So 18.88 plus, and if I just want to rewrite this where it looks a little nicer, we'll put 24.986x plus, now it gets to kind of the ugly part. If I'm distributing, I'm going to multiply this by 0.213 and by negative x. So we start with 0.213 times 25.983. Okay, I get 5.53, so on. We're going to keep 366, so 5.53 is fine. 5.53 is what this times that is, minus, and then x times that is just 25.983x. Okay, so we're down here. I can take it one step farther and combine like terms. So we're going to do 24.305 equals 18.88 plus 20. Oh, actually that's not. We don't know what that is yet. We're going to do that now. 24.986x minus 25.983x. I missed a minus sign in there. 24.986 minus 25.983, negative 0.997. Okay, so I'm going to cross that out. I know it's kind of sloppy, I'm sorry. Negative 0.997. So 18.88 minus 0.997x plus 5.53. Now we could combine some like terms. We could do 24.305 minus 18.88 minus 5.53. I get negative 0.105. Equals negative 0.997. Okay. So now that I've got that, oh, it's 0.997x, don't forget the x. I almost goofed up there. So you really, when you get this many numbers, you really got to go back and double check and make sure you're keeping track of what your like terms are. I almost messed up there and left it without correcting. Okay. So now I've got negative 0.105 equals negative 0.997x. If I want to solve for this, of course, I need to divide by whatever is multiplied by x. So that's negative 0.997, dividing on both sides. When you do this, 0.105 over 0.997, you get 0.105. So x equals 0.105. Okay. We just solved for x. That's the abundance of magnesium, 25. So we could say as a percent, of course, we need to multiply that by 100. So we have 10.5%, and our abundance, our isotope is magnesium 25. I already know the abundance here is 78.70. So to find y, we just need to plug that in. Y equals 0.213 minus x, so it's 0.213 minus 0.105. Excuse me. 0.213 minus 0.105, you get 0.108. And again, if we turn that into a percentage, it's going to be 10.8%. And our isotope here for Y, which is what I just solved, that is magnesium 26. All right. I hope that this was helpful. You guys can skip around. You could watch it again if you want to. I just wanted to make sure I went back through this in a way that you could watch the whole process again and make sure you're comfortable with it. Now try your hand at the rest of that worksheet, the practice worksheet. It's really similar to this, isotope abundance practice. And I will be back on Wednesday, so hope you guys have a good weekend, and I hope that you have a really productive week. Times 24.9.